Two of the things that humans have always done are make things and go places. Sometimes we go places to make things, sometimes we make things to go places. One place I like to go to make things is right here. Specifically, I've worked on 3D printed humanoid androids. I've worked on scale models of brain implants, mechanical dreadlocks, little models of creatures or machines that are just being tested out at first and then make their way up. Almost never do we use 3D printing to make a final product that's going to go somewhere. Until this semester, when the IREC team, as part of the Autonomous Robotics Club, designed and built a drone that can be folded up, loaded into a rocket, and sent to other worlds, with the goal of surveying other planets. We had to start out with something a little strange. We were hoping to fold it up sideways and put it in a box. The wings out like this, the body here, and a big old battery pack on the side. That way the drone could come home every now and then after taking a few pictures of the planet and charge up. But we realized it would be too small, it couldn't carry anything, so we made it a little bigger. By this point in our process, the rocket is 12 feet long, 8 inches in diameter. And instead of folding up sideways, our drone folds up like this. The props pointed inwards up at the top. And instead of letting the rocket land and then unfolding and flying, which could lead to some very unpredictable situations depending on terrain, the rocket will explode at apogee, at the highest point in its arc, or, in the case of exploring other worlds, as it's entering the atmosphere. The top part will open up a parachute, and we will be lowered out by a telescopic arm. And at the very bottom, we unscrew ourselves from the end of the arm. As our arms unfold, the rotors start up, and we fly the rest of the way down to a safe height where we can start taking pictures. The solar panels are now loaded directly onto the arms, meaning we can charge as we fly, and if things get a little rough, we can set down somewhere and just wait it out. Now, I'm not entirely sure I've made it clear how enormous this drone is. This is the body. This part here. It's held together with threaded rods, which allow us to control the height of the plates in the middle that hold our electronics, which also have a hole down the middle for where our enormous battery pack will be going. And then out from the top of this, in these 4 slots around the octagonal upper shape, we will have folding arms. They connect like so, where there are skater bearings on either side, and it will start folded up like this, with an elastic band connecting the wrist, so to speak, down to the underside of the top, constantly forcing those arms outward. Once it's outside of the tube, it's free to fold down, but how are we going to keep it like that? It's just sort of on a skater bearing, and the motors can just as easily pull it right back up. So we devised a system with 3 small holes in the bottom of the arm, inside of which we will have hardened steel pins connected to tension springs, ready to go. The tips are rounded so that they slide smoothly across the inside of that socket, and then once they're aligned with the hole, they pop into place. And once they're in there, there's nothing that will get them back out, except for a person going in on the other side and driving a small bit through the other end. Which will mean that once our drone is deployed on whatever world we're sending it to, it's open and going, which is exactly what we want. We want to be able to look at the surface of this other planet for as long as possible. Now, for testing purposes, this other planet is New Mexico. But hypothetically, this could be used on any planet with a gaseous atmosphere. Hypothetically, even Mars, depending on how strong the motors we get are. Our current model should be able to carry our drone for several hours over a desert. However, in the thinner atmosphere of Mars or Mercury, it wouldn't be so easy. We are, according to our project plan, about 80% done with the current design. But we're constantly redesigning it, finding more redundancies that we can insert and have ready to go in case any of those pins snap or in case the arm itself breaks off. That's our biggest challenge right now. Because while 3D printing is amazing and strong, not all materials are extruded equally, so to speak. Right now we're looking into nylon-infused ABS and nylon-infused PLA, but there are stronger materials such as carbon fiber and printed metals, which are considered, though the cost is a little out there for us. At the moment, we should be ready to launch by next summer. Not this coming summer break, but the one after. And all along the way, we'll be improving upon this design. Are there any questions on this project? Thank you very much.
Isaac, it's a teamwork or individual, or how many teams you have? Or
we have, so this competition, the IREC competition, is team-based. There's teams from different schools. Some schools may have multiple teams, but ours is one team of, I think, 8 people.
Shane is a part of it or not?
Shane is a part. We've also got a few new-coming ECE majors, ME majors, sort of all over the board. People designing new parts as.
Do you ask some budget from SMAC in Chapter 606, or how do you afford it?
We did ask for a bit of a budget. Thankfully, due to the efficiency of 3D printed materials, we haven't had to ask for too much. But most of that budget did go into the metal components like the solid steel plates, the battery.
For the fall, are you going to be around?
I'll be here in the fall. I'll be working on this in the fall, but I graduate in December. Yeah.
You have two options. Number one is Ed Lisick from the chemistry department. If you schedule an appointment and debrief this to him, what you do, and ask some budget, every penny helps. And number two is Chapter 606 in EGOS. And if you file it, you can cover up almost all expenses. Just keep me in the loop if you need anything. And please consider these two sources. University is available for you to support with those.
Did you say Dr. Lisick?
Ed Lisick from chemistry. He leads the university undergraduate research programs. And the other one is University Chapter 606. And I think Mark Burnett handles it. And then they give really hard dollars.
I actually know Lisick personally.
So Ed Lisick is just wonderful. He's the best faculty you could ever have in this campus. Go and debrief him, this is what you do. He has some budget, he could. If not, Mark Burnett, Chapter 606, then this way you can grow. You can grow.
Sounds like a good idea.
Wonderful project. Wonderful. Great.
Here you go. So hopefully this prints many more parts of your drone. We look forward to following this project. This one's one of my favorites.
Yeah. Excellent.